Hello, calculus students and general seekers of truth. Welcome to the lesson on limits and continuity. And let's begin with our intuition of what continuity really is. In most cases, it's usually described as being able to draw a graph without any breaks or holes in it. And that is a pretty good description of what a continuous graph should look like. I'll draw some examples here, and then we'll get into some more technical and precise language, just so that we are using mathematically correct terminology. So let's discuss next, what is removable versus non-removable discontinuity. Well, removable basically means that you could fill the gap or fill the hole with a single point. Alright, so say you had a graph like this graph of f of x, and there's a hole here at, say, x equals 3, then in this case, this is a removable discontinuity because we have a hole at x equals 3. Now, there are other cases where it is non-removable, and this basically means when you have a big jump or when you have some sort of vertical asymptote. Alright, so like in the second graph that I have here on the right, we can see that when x is equal to positive 1, what we have here is a vertical asymptote, and we'll call this an infinite discontinuity. Okay, because you have things shooting up to positive infinity, or you could have curves that go down to negative infinity. And here what we have is what's called a jump discontinuity. Okay. So that's just kind of the three types, but we can categorize them as removable and non-removable discontinuity. Okay. And in previous classes in Algebra 2 pre-calculus, this is pretty good. This is about all that we have to say about continuity. But in calculus, we have to really take this a step further. And so now I'm going to give you a formal definition of what it means for a graph to be continuous at a particular point, so at a point C. So a function f of f is continuous at some point C if and only if the three following conditions are met, and all three of these conditions have to be satisfied. Okay, so all three conditions have to be satisfied. So first, Roman numeral 1, the limit as x approaches c of f of f exists. We've talked about what it means for a limit to exist before. 2, f of c is defined. And 3, the limit as x approaches c of f of x is equal to f of c. So the limit exists. It approaches some point as we get near that value c. F of c at that point is also defined, and the place that it approaches the point is equal to the place that it is at the point. So that was very, very wordy there, and I'm just going to use this picture below here to help illustrate a few things. Let's just make this, just for simplicity, let's make this scale here 1 by 1. Okay. So let's see. At x equals -1, -2, -3, at x equals -3, you can see that we have a jump discontinuity, so condition 1 fails. Because the limit from the positive side and the limit from the negative side are not the same, therefore the limit does not exist. Here's another good example. At x equals 2, the limit does exist. The limit as x approaches 2 is -1. However, f of 2 is undefined. So we can say that condition 2 fails. Okay. And if either of these first two conditions fail, the third one will also fail. Now, at x equals 1, 2, 3, 4, you can see that condition 1 is satisfied as we approach 4 from the negative side and 4 from the positive side. The limit is equal to 2. F of 4 is -1, -2, -3, right? So just to be clear, the limit as x approaches 4 of f of x in this case is equal to 2. F of 4 is equal to -3. But however, you can clearly see here that condition 3 fails. Okay. The limit exists, f is defined, but the limit and the value of f are not equal to each other in this case. So there's an example of all three cases failing. And let's pick a case where it does work. And it's not hard to find. Let's pick this one right here at x equals -1, -2. Okay. So at x equals -2, you can see that the limit approaches 2. F of -2 is 2, and so they're equal. So here it is continuous. In the other three cases, it is not, right? And this is kind of a lengthy way to do things, but hopefully it does illustrate for you why all three of these conditions are true. And you can see that why all three of these conditions really are necessary for us to have continuity, even if we were to use the intuition, right? For there to be a smooth curve like this, there has to be a limit, there has to be a point. The limit and the point have to equal each other. So I'm going to end this video here, and I will start another video that will walk us through some analytical examples.